So Risk is a board game, and these little, it's kind of an abstract kind of war game. And these are pieces. All right. So, John, you know this game. So what's the difference between, what's this? What is this?
That and that.
Yeah, what's that and what's that?
It's been a while since I played.
Oh. You know? You don't remember? Oh, man. All right. So this is an army. Kind of an abstract army. It's plastic, but it's really just a piece of plastic. This is 10 armies. Right? By the time you get to the place in the game where you use these, it's almost all over. Here. So why 10? I guess we all know why. I mean, we have this system where we'll write down some number, 632. We definitely don't mean 632, do we? Right? I mean, where the number is special, right? And that's a 2, and that's 3 Death Stars. That's what we used to call these, right? That's really 30. And that, of course, is 600. You all know this. No big deal. Early numbering systems didn't use this system. You needed a different symbol for tens or hundreds, except they didn't use tens and hundreds. They used like 60s or, you know, Roman numerals, right? 5, 10, 50, so forth. But where this comes in is, today is, we're going to do something called long division. Now, I asked in the other class, everybody claimed they learned long division. Has everyone here learned long division? Right. There was a period where it was going out of style, and I heard some grammar school and high school teachers saying, oh, they don't need to know how to do long division. Yeah, I don't agree. But how did we do long division? Well, kind of write it like this. Maybe if we want to be really orthodox, we'll kind of go like that. I know you all know how to do this. There's a point. So 3 into 6, well, that goes 2 times. So we multiply 3 times 2. Again, not really 6, is it? 600. But it's okay. We subtract. We bring down the next number. 3 goes into 4, 1. We have 3. Oh, now I do have something like 17. Times 5, 15. Now I'm done. I've got a 2 here. We can either write that as remainder 2. That's how you do it like in 5th grade when you're learning, or 4th grade when you're learning this. Or, you know, when we get into high school, we'd say that's 2/3. Right? So that's how long division works. Very oriented towards, you know, columns and placeholders and but the long division I'm talking about is not like this. I'm talking about a long division of polynomials. So, for example, you might have x squared minus 26 plus 12. You might want to divide that by x minus 4. And we're going to look at a couple ways of doing this today. The first way is the old-fashioned way. It's the way I learned. But we're also going to look at something called synthetic division, which you may be better at than I am, because I didn't learn it in high school. We'll talk about that. Does anyone here not know synthetic division? When I ask a question and nobody raises their hand, I don't actually nobody didn't learn it, but maybe. They're thorough when they change things. All right, so how do we do this? Well, the old-fashioned way. The next goes there. 6x squared minus 26x plus 12x minus 4. It looks pretty much the same way long division of numbers. You look at the x and you say, how many times does that go into 6x squared? Well, it goes in 6x times. We multiply. This better match, so it drops out. Minus 24x. A little digression here. I have noticed that some of the students in my class have trouble with negative signs and subtracting. Something you might want to do is just convert, to give you some way of focusing in on that problem. If you don't have a problem with it, don't worry about it. Okay, so here, negative 26x minus negative 24. Very clear what I'm doing. Negative 26 minus negative 24 is negative 26 plus 24. So that's just minus 2x. Bring down 12. Okay, this is going to go in what, minus 2 times. Minus 2x. Minus 2 times minus 4 is 8. Get my remainder. And I'll just say 4 over x minus 4. That's how I do long division. It's a little clunky. You got to keep writing all those x's. Gets the job done. It has an advantage over synthetic division. There's something you can do with this that you can't do with synthetic division. With synthetic division, this has to be what? It has to be first degree polynomial, coefficient 1, right? We'll get to synthetic division in a minute. But I'm just saying there are things you can do this way. So you need to know how to do long division. But because it can do everything synthetic division does, you don't need to know synthetic division. Synthetic division is nice though, because it's so easy. We'll get to that in a second. Just one more comment on doing this carefully and accurately. If I had something like this, x to the fourth plus 6x squared minus 3x plus 1 over 2x squared minus x plus 2. Well, there's a term missing here, right? It's a zero term, right? So when you do this, please do not forget 0x cubed plus 6x squared minus 3x plus 1. Because, again, this is all kind of very based on these columns and everything being in the right order. Otherwise, you can mess it up really easily. All right. Let's look at synthetic division. We're going to take this problem. 2x squared, no, 2x cubed minus 7x squared plus 5 divided by x minus 3. So how we set this up is first we write down the coefficients. 2 minus 7. Oh, wait. I'm missing something here. 0 plus 5, right? I'm missing something. And what I write over here is not minus 3, it's x minus 3. I write down 3. Okay. So step 1, I take this 2 and I write it down here. It's pretty easy. Next step, I multiply 3 times 2 and I write it here. Then I add. I repeat. 3 times minus 1 minus 3, I add. And then I have to do it one more time. 3 minus 3 is minus 9. I get minus 4. Okay, now I have to know how to interpret this, right? Well, these are the coefficients of my quotients. 2x squared minus x minus 3. And there's my remainder. All right, that's great. It's really easy. It's kind of like magic. Problem is, I don't really know what I just did. I don't know why that works. Not yet. We're going to get to that today, but well, one thing I want to mention about this, when we say this equals this, right? Another thing we're saying is that 2x cubed minus 7x plus 5 is equal to x minus 3 times 2x squared minus x minus 3 plus minus 4. Does everyone see that? It's just the, you know, you take this equal to this and multiply by x minus 3, you get this statement. Right? That's what dividing is, right? means after you divide, if you just multiply back and add the remainder, you get what you started with. All right, well, I am interested in why this works, and I'm interested in showing you. But before we do that, we need a little machinery here. So let's start building some machinery. We're going to start really slow again. I'm just going to do a simple division. Say, I don't know, 19 divided by 7. So I'm going to divide the long way. 7 goes into here twice. 14, it remains 5. So what that means is that 19 is equal to 7, what I'm dividing by, times 2, plus my remainder, which is 5. Well, you could call this the remainder theorem of numbers. I don't know if they actually do. But what we're going to be looking at is the remainder theorem of polynomials. It's very similar. It says that if I have a polynomial and I divide it by first degree polynomial, right, with a coefficient like this, that what I'm going to get, remember I didn't say anything about what this polynomial is like. I'm going to get another polynomial, we'll call it q of x, which will have a lower degree, right? This is degree 5, and this has to be less than 5. It could be 4, 3, or... But also, we might get a remainder. This seems pretty straightforward. It does really require proof we're not going to do, but I think it's clear enough. Again, I want to rewrite this because equivalence statement is that p of x equals x minus c u of x plus r. This is not the remainder theorem. This is just something we need to show the remainder theorem. So what is the remainder theorem? The remainder theorem of polynomials says if p of x is a polynomial and we divide it by x minus c, then the remainder is going to be equal to p of c. In other words, if you have a polynomial, you want to divide it by x minus some constant, and you want to know what the remainder will be, you just plug in c. That seems pretty amazing. Let's check that out here. I divided this polynomial by x minus 3. I got a remainder of minus 4. If I plug minus 3 in here, what do I get? 2 minus 27 minus 7 times 9. This never works out when you want it to. I'm sorry. I have to plug 4 in, right? No, plug 3 in. So this is plus 27 minus 9 times 7 is 63 plus 5. So 54 minus 63 plus 5. Oh, that's minus 4. Exactly what I got. Miracles. Anytime I do something right on the board, it's a little miracle. Okay. But we don't actually just have to try a bunch of test cases to see if this is true. This is actually fairly easy to show. It's fairly easy to show that if you divide p of x by x minus c and you get some polynomial q of x and a remainder, that merely plugging in c gives you the remainder. How do we do that? Well, this is a restatement of what I just said. If I plug in c here, I get c minus c times q of c plus r. C minus c is 0. Q of c doesn't matter because we're multiplying by 0. This is just equal to r. Once again, I plug in c, and I get the remainder when dividing by x minus c. That's the remainder theorem. Let's try and just try one more example. Just see if this really works. Or see how it works. Let's take polynomial 3x to the 5th plus 5x to the 4th minus 4x cubed 7x plus 3. And I want to divide p of x by x plus 2, which means my c is minus 2. And I want to know what the remainder is when I do this division. So according to the remainder theorem, I just have to plug it in. Okay, now we have to do a little math. Negative 2 to the 5th, that's, computer people, you should know this. Just look at it. Aha, that must be negative 32. So negative 96. 2 to the 4th, 16 times 5 is 80. Minus plus negative 2 cubed, that's negative 8 times 4 is negative 32, plus negative 14 plus 3. Okay, that's negative 16. That's 35 minus 14 is 21. Equal to 5. It's pretty easy compared to doing that long division. If all we want to know is the remainder, it's pretty easy. Okay. Any questions so far? I told you there was a lot of moving parts today. The next moving part is called the factor theorem. Factor theorem. Factor theorem is a corollary of the remainder theorem. We found out that a lot of students took geometry a long time ago and they forgot what a corollary is. So I'm going to ask, does anyone here know what a corollary is? Jessica, you look like you might know. No, I'm misinterpreting the look. Yes?
Proposition and follows one already.
It's very good. There is a lesson here, you know. Sometimes if you know just a little bit more than everyone else, like how to use Google, you're the genius in the class. Too bad we couldn't just like do all our exams that way, right? We just type the question into Google and get an answer. Yeah, the factor theorem follows very simply from the remainder theorem. So what is the factor theorem? It says if did I write this right? Okay, there it is. It says C is a zero of P of X if and only if X minus C is a factor of P of X. All right. Break this down a little. C is a zero of P of X. That means you plug C in and you get 0, right? X minus C is a factor of P of X. That means you divide by X minus C and you don't get a remainder. Right? It's one of the factors. Is everyone familiar with this abbreviation, IFF? Stands for if and only if. Be ready. You might need to Google this. What does if and only if mean? You don't get to answer first. Somebody? Yes?
There's only two groups.
Hallelujah. This is a religious institution, so I can say that, right? You need 2 proofs. Okay. What are the 2 things I need to prove here? C, if C is a zero of P of X, then X minus C is a factor of P of X. That's 1. Then you got to go in the other direction. If X minus C is a factor of P of X, C is a zero of P of X. This corollary was supposed to be simple. Simple extension of the remainder theorem. Looks like a lot of work. All right. Let's give it a try, though. This is one of those proofs where, in a way, it's so simple that it can go right by you. Go right by. It's like, it's too easy. Okay, from the remainder theorem, we know that if I were to divide P of X by X minus C, then I get some Q of X, which I can multiply by X minus C and just add the remainder. Right? That's what the remainder theorem says. So let's start with if C is a zero of P of X. Well, that means that P of C equals 0. But P of C is equal to Q of C times C minus C plus R. Well, this is 0. This is 0, so we have 0 plus R. We conclude that R is 0. So if C is a 0 of P of X, then I know that P of X equals Q of X times X minus C plus 0, right? Well, what does this statement mean? It means X minus C is a factor of P of X. So that's the first part of the proof. If C is a 0 of P of X, then X minus C is a factor of P of X. Okay? That's part 1. We have to start the other direction. What if X minus C is a factor of P of X? So how would I write that? I would say, well, P of X is equal to X minus C times some other polynomial, Q of X. Right? This is the really easy part. What I want to know is, what is P of C then? P of C is C minus C times Q of X, which is obviously 0. So C is a 0 of P. Get that? If X minus C is a factor of P of X, then clearly P of C is 0, meaning C is a 0 of P of X. So that's the factor theorem. It goes in 2 directions. It's 2 theorems. All right. All right. We needed the remainder theorem and maybe the factor theorem for the next part. I want to go back to this guy here, synthetic division. I want to figure out what's going on here. But first, you know, we have some computer science people here. Raise your hands. Yeah. At least a third, maybe more. So you guys program computers, right? And you tell the computer, let's see, take 3 and 5 and multiply by 6 and subtract 4 times 7 divided by 3. Right? Computers don't really understand what this means. Now, computer languages do understand what this means. But, you know, inside the computer, there's circuits, and there are instructions, right? There's an add instruction and a multiply. But there's no parentheses instruction. This is kind of an extra for you non-science, computer science people. So how do we get this? How do we turn this into something that the computer can actually do something with? Anybody know how we do that? While you're thinking, I'm going to catch up on attendance here. There we go. Can I see Shane Ping come in? No? Okay, Daniel's here. Eduardo, is Eduardo here? Okay. Elliot, is Elliot here? No. And Blade is not. Okay. Anybody knows how that happens? It's magic. Yes?
Like, I know for functional programming, you'll return, so like 3 plus 5 and 7 divided by 3 as separate functions. So you call like A and B, 6, A, B.
See, that's a computer language.
Okay.
I mean,
Yeah.
it's a good answer, but I'm really wondering how the computer does it. You know, you guys may not have had to drill down to machine language yet, but the computer really is dumb, down at the bottom. Someone else have something you're going to say?
Just
Okay, that's the best answer so far. We simplify it, but we simplify it in a certain way. Right? The technical term is parsing. You parse this, figure out what it's doing, and then you translate it into something the computer can do. Like you might have a compiler program that does that. You might have an interpreter. But the way the computer is going to get this is it's going to go, it might look something like this. You might say push 3, and then push 5, and then add. In other words, add those two things I just pushed into my stack. If you don't know what a stack is, don't worry. And then I might push 6 in, and then I might multiply. And then I might push 7 and 3 and then divide, and then I might push 4 and multiply, and then I just subtract because my answer stays the same. The point being, I'm not like adding and subtracting the way we do. Like we say 3 plus 5 equals 8. What a computer really likes, because it's nice and logical, is 3, 5, add. Right? And then I could say like 6, multiply. And you really can do this inside a computer. This is sometimes known as RPN. You know what RPN stands for? Somebody's whispering. I can't hear them whispering. Well, the R stands for reverse. It means reverse Polish notation. I don't know why. They used to sell, Hewlett-Packard used to sell an RPN calculator, which was really cool, except people didn't like it, so they don't sell it anymore. Look on eBay. You got that? RPN, HP, they were great calculators. All right. Why am I telling you all this, all right? Like you said, there are a lot of moving parts here. I want to go finally back down to synthetic division. I'm going to write down my problem here. 2x cubed minus 7x squared plus, I don't want to forget my x term, plus 5. And I want to rewrite it a certain way. So first thing I'm going to do is I'm going to take an x, I'm going to factor an x out, but I can only factor it out of these 3, so that's what I'll do. 2x squared minus 7x plus 0 plus my 5. And then the next thing I'm going to do, I'm going to do that again. I'm going to take out an x, but I can only take it out of these 2. So what do I get? I'm going to get x times 2x minus 7 plus 0 plus 5. And then I'm just going to do it one more time. X Now this is my p of x, right? And I want to find out what p of 3 is, right? Because the remainder theorem tells me that's what I need to do. I need to plug in 3 here. But I want to do it very carefully and slowly so I don't make a mistake. So I'm going to start by just plugging it in here. Okay, so I'm going to multiply 3 by 2. Now I just want to make a note. When we were doing synthetic division, we multiplied 3 by 2. We got 6. Let me put it here. Okay. So, 6. And then, you notice I just had to do 2 operations, 3 to multiply. Now I know what to do next. I have to add 6 and minus 7. So I'm, however you like, either I'm going to subtract 7 from 6, or I'm going to add negative 7 to 6. I'm going to add negative 7 to 6. Right, so that I multiply 3 by 2, that one here, negative 7 plus 6. Okay. X minus 1 plus 0 plus 5. Okay, what happens next? Well, now I'm going to plug 3 in again here, right? Because I have to replace all these x's with 3's. So I'm going to multiply 3 by minus 1. 3 times minus 1, and I get minus 3. Right? And then what am I going to do? I'm going to add 0. 0 minus 3. Okay. X 3 minus 3 plus 5. And now finally I'm going to plug in 3 the last time. Right? 3 times negative 3, and then I'm going to add 5. See, 3 times negative 3, I get negative 9. Add 5, and I get minus 4. A lot of moving parts here. So what just happened? Well, for you computer science guys and gals, if that's not pejorative, ladies, women, that's it. Okay, now I'm on track. I kind of arranged this so I can do kind of an RPN calculation, right? I just have 2 things and I compute, multiply, add, right? And I noticed that in the process of calculating p of 3, which I know will get me the remainder, right, from the remainder theorem, I find that I'm doing exactly the same calculation that synthetic division does. See, in a very complicated, well, not a complicated, a very simple way of hiding what's going on, synthetic division is using the remainder theorem to calculate the remainder. That's what I get over here. However, along the way, as I start out, you see there's a 2, right? That's the coefficient of the polynomial of the quotient. Minus 1 kind of pops up over here. And then finally minus 3. So I'm actually doing a little bit more than just using the remainder theorem. I'm picking off these coefficients as I go along. But it's kind of a big deal. I mean, somebody came up with this really simple kind of way. plug in 3 and grab these. All right. That's kind of big news for today. Let me back up a little. So, what is today about? You need to know how to do polynomial long division, right? Just knowing synthetic, I could have written synthetic division. If you know synthetic division, hoo-ha, great. Just know when to use it, how to use it. It's actually much simpler, but it's limited. You only get to divide by x minus some number, which we're going to do a lot. If you don't know how to do synthetic division, you will not find a problem on an exam that says, do this division by synthetic division. I don't. It's redundant. It's easier, good. If you know how to do it, great. But don't worry about it if you don't. You need to know the remainder theorem of polynomials. You need to know that to divide by x minus c, find the remainder, you can just plug c in. And you have to know the factor theorem, which says that if you plug in a c and you get 0, then x minus c is a factor. I think the other way is kind of obvious. If x minus c is a factor, obviously if you plug in x minus c, you get 0. All right, let's do an example of how you would use the factoring theorem to factor a polynomial. So I have a polynomial here. It's third degree, so I don't necessarily know how to deal with that. It can always be a problem. If it's fourth or fifth degree, even more likely. For today, we're gonna do a little cheat. By that I mean we're just gonna guess. We're gonna try and guess a root. So I always guess 0 first, right? 0 minus 0 plus 6. It's not 0, so 0 is not a factor. That's kind of, from the mathematical journal of duh. But if I try 1, what do I get? 1 minus 7 plus 6. Right? F of 1 equals 0. Well, that tells me right away that x minus 1 is a factor. At that point, I can either use long division or synthetic division and find out what's left. The other class I did long division. I'm going to challenge myself here, because I'm not so good at this. 1, 0, negative 7, 6. 1. Okay. Catch me if I make a mistake, because like you say, you guys know this better than me. Bring the 1 down and multiply. That's 1, 0, 1, 1, negative 6, negative 6, negative 6, 0, yay! It better come out 0, right? Because the remainder better be 0. All right, so this tells me that f of x is equal to x minus 1 times x squared plus x minus 6. Okay? Whenever we get down to a quadratic, life gets really easy. We don't have to fiddle around or anything. I mean, maybe we can do simple FOIL on this, maybe not. But even if we can't, we can always use the quadratic formula, right? Quadratic formula is going to find the zeros, right? And by the by the factor theorem, if I find a 0, x minus that factor, x minus that 0, not sure if I said that right. Anyway, I'll find the factors. So let's do it the hard way here. Let's use the quadratic formula. B is 1, so -1. Plus or minus the square root of 1 minus 6, right, times 4 is plus 24 all over 2. So -1 plus or minus 25 is 5 over 2. So what's this? Minus 6 will be -3, and 4 over 2 is 2. Ah, so my roots, my zeros are -3 and 2. So now I know that f of x will be x minus 1, x plus 3, minus a -3, x minus 2. The cheat here is I had to guess that first value, right? How did I do that? It might not always be easy. On Wednesday, we're going to learn what to guess. Foreshadowing here. All right. Afraid you guys are just too good because I don't have any more for you today. I'll hang around if you have questions, homework, or whatever, and I have office hours this week. Yeah, homework to turn in, now would be time.